So now let's think of an experiment we could do that would help us determine what Planck's constant is. Now, it's very difficult to do the experiment in the labs we've got. Well, there is a device we've got that can do it, but it's not very impressive actually. So you might want to use that PhET simulation if you wanted to get some results to see how it works. But basically what you do is you get your particular metal, you change the frequency of the light that you shine on it, and you measure, using a stopping voltage, you measure the kinetic energy of the electrons that come off it. So choose a frequency, shine the light, measure the kinetic energy of the electrons. Change the frequency, shine it again, measure the kinetic energy of the electrons. Now, change the frequency, measure the kinetic energy of electrons, and so on and so on and so on. So you get those two results. You've got the frequency and you've got the kinetic energy. Now, let's go back to what we were looking at before. We said that HF equals the work function plus the kinetic energy. Okay, so what we could do is write it this way around, just to start with. Why don't we write it as phi plus EK equals HF. And then from there, what we can do is very simply, we can say kinetic energy equals HF minus phi. Now look what we've done. We've got ourselves a straight line graph there, haven't we? Because what we've got is we have got this bit is going to be y, m, x, and c. So in other words, if we were to plot a graph like you can see here of kinetic energy on the y-axis and frequency on the x-axis, because we've got y going there, we've got x going there, what we will find is the following. We will find that the gradient of the graph will tell us Planck's constant. So that is how we could determine Planck's constant experimentally. Okay, so really quite clever. So that is the gradient is Planck's constant. And also it tells us that the intercept, the y-intercept there, so C, the y-intercept, is the negative of the work function. As you can see here, you can see that the intercept is a negative number. So let's say it was -3. Well, that would mean that the work function is +3. Now, what is interesting is, and that's why I like this second graph here, is we've got two surfaces. One metal gave us this set of results. Another metal gave us this set of results. Now look what it tells us. What it tells us is the gradient's the same on each, because that means Planck's constant's the same for each, because Planck's constant's a constant. But what it tells us is that the threshold frequency here for photoelectric surface number 2, for the metal number 2, and the one here for metal number 1 are different. So where it crosses here, that was the frequency, because below this frequency nothing happened, and at this frequency we started to get the effect, so we can figure out what the threshold frequency as well. So that's what it means that's what it means in the syllabus when it says be able to answer problems graphically about this.